All right, so we're going to talk about titrations of weak acids. If you are in standalone, you will have a lab on this. If you are in integrated, then you will be spared from this to some extent. We've been working on equilibria, and titrations really bring together everything we've learned in equilibria. Whether or not we've learned buffers, titrations bring in the Henderson-Hasselbalch equation. So if you haven't heard that, you'll probably hear that at our next lecture. They bring together those rice tables under different conditions. They bring together some of our CHEM103 topics with the pHs of strong acids and bases. It brings in stoichiometry. So lots of different components here, which makes them really good systems to kind of explore our knowledge and understanding of chemistry. So previously we've looked at vinegar as a weak acid. So vinegar has the molecular formula CH3COOH and a pKa of 4.74. All right, so that probably doesn't mean a ton to us yet. A pKa is basically how much affinity does acetic acid have for its protons. If you are above the pKa, so you're more basic, it will lose its protons. It doesn't have enough affinity to keep them from being pulled off by the bases in the water. If you're below that pKa, if you're more acidic, then those protons come on, right? And hopefully we recognize this COOH is kind of our organic functional group. And so we could draw this compound. Now, if we're thinking about acidity, then this hydrogen is our acidic hydrogen, our acidic proton. This is the one that we're going to lose. So if we were to write a weak acid equilibria for vinegar, it would look something like CH3, COOH. We could include water if we want to. We don't necessarily need to, so we're not going to put it there. So we'll break up into CH3, COO minus, and H plus. So that H plus will come off on its own. If we think back to our CHEM103 topics here, these idea of Lewis structures and structural resonance, this group here, this is our organic acid, right? So we can write any organic acid, or at least carboxylic acid, as this. If we give up that proton, we're going to make an O minus there, right? And really what that means is that we have an extra pair of electrons. Let's circle this one. An extra pair of electrons on top of this oxygen. Well, when we draw this Lewis structure, or if we redraw this Lewis structure rather, this pair doesn't have to end up here. We could draw this pair down here and show one of these pairs exiting onto that oxygen, and we could rewrite that moving that lone pair group up to here, right? So we have this nice resonance that happens anytime we have a COOH group. So anytime you see a COOH group, that's going to be a weak acid. This is where that comes from. That is our nice 3.5-minute detour on why vinegar is a weak acid. So vinegar is a weak acid. We know it's pKa. Let's ask some questions about this. So if I have, let's say, 50 milliliters of a 1 molar vinegar solution, what's the pH? Right? So this is where we think of our rice tables, right? So we have our reaction, our initial. Why don't we write these in all the way, right? So reaction, initial, concentration, that's in molarity, change, that's in molarity, and equilibrium concentration, also molarity. We have up here our vinegar, right? CH3COOH, that's equilibrating to make CH3COO minus and H plus, right? Told those initial concentrations. So we have 1 of that. Because this is in molar, I don't have to worry. If this was given to me in millimolar or something, I would have to convert it to molar. So regardless of what concentration unit you're given, these rice tables, which are going to kind of pair with the Ka. Ka is defined relative to the normal state, which means 1 molar concentrations. So everything in here has to be also in molar concentrations. We're going to start with 0 CH3COO minus and 0 H plus, right? Because our assumption for this initial condition is that we're starting here and we want to know what happens at equilibrium. So because we have no products formed, we know this reaction is going to go to the right. We're going to lose reactants, we're going to make products. So at equilibrium, we're going to have 1.0 minus X, and we're going to have X amount of products. So lastly, we just need to relate these somehow. So this is where our Ka expression comes in. Remember, our Ka is equal to our products over reactants raised to their respective X stoichiometric coefficients as exponents. So here we're going to have, and for acids and bases, because we only look at these as monoprotic dissociations, they're all going to have this format. All right, we're going to have conjugate base raised to the first times the H plus, so times the proton concentration divided by the amount of vinegar present, the weak acid. So in this equation, we weren't told the Ka, we were told the pKa. I know that Ka is just 10 to the negative pKa, 4.74, right? So 10 to the negative 4.74, and that's going to give us 1.8 times 10 to the negative 5. All right, so now we have enough information to set up and solve this equation, right? So we have 1.8 times 10 to the minus 5 is equal to X times X over 1.0 minus X. And so now we just solve that for X. I'm going to, as always, just turn this over to Wolfram. So, you know, there are 3 ways to solve this, right? We could solve it using the quadratic equation. I guess there's 4 ways. All right, so we have 4 ways to solve for X. All right, so our first way, we could expand this and do a quadratic equation. We could make an assumption. We could test an assumption about X and assume that X is much, much less than CH3COOH. And if that's true, then that means that CH3COH minus X is roughly equal to CH3COOH, right? Vinegar, this quantity would still be equal to 1 in that case. Our third option here, do I really have a third option? Fourth option? I really thought I did. There's probably some like complete the square shenanigans you could do here, but we won't worry about that. Let's not worry about that. So I guess we're going to become 3 ways to solve. And our third way to solve is just use software. And that'll give us either a computational or a symbolic solution. In Wolfram Alpha's case, that'll give us a symbolic solution. I have Maple open on the side here, but why don't we just open Wolfram real quick? All right, so we're just going to take our lovely equation that we've set up here. Why don't we, 1.8, I like to use engineering notation because I'm lazy. 1.8 e to the negative 5, which is the same as times 10 to the minus 5. It's just one letter instead of a whole bunch, and you're less likely to get errors there. We're going to use our natural language, our math input here, x squared over 1 minus x, right? And then we solve for x, and we get 2 roots here, right? Because this is a quadratic, it should have 2 roots. We have a positive root and a negative root. Assuming we set up our directionality of our balanced equation here correctly, we want the smallest positive root, right? And you can test other roots, like, you know, if we put negative here, that's saying at equilibria we have negative concentrations, which isn't possible. If your roots are too large, if you have 2 positive roots, the larger root's usually so large that subtracting it from, or is always so large that subtracting it from your initial concentration would make that negative, so that's not possible either. So you do want to test that the root you select is physically possible, but generally the smallest positive root is the only possible answer. All right, so now we can copy that over, and we get x is equal to 0.00423. All right, and here we have 2 sig figs because our Ka only has 2 figs, our 1.0 has 2 sig figs, so we'll just mark that. If we want to know the pH, well, we know that's equal to our H plus concentration pH is just the negative log of H+. So we can just plug that value in. This is where we're going to use our buddy maple here. Oh, no, we're not going to use maple here. So the one issue I have is that maple, if you type log into maple, it will treat it as a natural log unless you specify base 10. Let's do the negative log of 0.0423. And let's hope that that works, right? That doesn't look good either. Yep, see, that is a log base E. All right, that's horrifying, right? Is there a log button down here? We've got roots. There we go. All right, so unfortunately, we are going to have to do log 10, 0.0423. And this is something you should always check if you're ever using math software. Check if it will treat log versus ln, because good stuff does, but a lot of really technical math programs don't. Like Wolfram doesn't, Maple doesn't. So just make sure you're using the right log, and that should make sense. And the reason we were suspicious about like the log being 5 is that implies your exponent is 10 to the minus 5, which would have more zeros than this, right? This has to be 1, 2, 3, right? So we're going to have an answer that's between 2 and 3 for our logarithm here. So in 2.37 makes sense. All right, so let's go back over here. So our pH is 2.37, right? And we did this exact example in class, I believe. Now we're going to take this to the next step, right? So that's the starting point. So in a titration, that's a neutralization reaction, right? So we're adding acid and base until we use up all our, let's say, acid, right? So if we're titrating an acid with base, we want to add exactly enough base to cancel out our acid. Typically, when you do titrations, you don't actually know how much stuff is there. So it's almost the flip side. In 103, you may have done a phenolphthalein titration where you had an endpoint where your solution changed color. That works really well for titrating acids, I think, because that color change is sudden and it's high pH. So we're neutralizing acid and base. And now the question is, what is the pH after adding X volume of base? So this is a challenging question, right? And let's think of a concrete example. So let's pull our 50 milliliters of vinegar again, right? So we have our 50 milliliters of 1.0 molar vinegar. Now, for the sake of argument, let's say we're titrating 1.0 molar sodium hydroxide, NaOH. Right, so vinegar is a monoprotic weak acid, CH3COOH. We're going to add NaOH to it. And remember, these are not equilibria. Neutralization reaction with a strong acid or base goes to completion. So we're going to make Na sodium acetate, NaCH3COO, and water, right? HOH, or just, H2O. So if we wanted to figure out how much sodium hydroxide we needed to add to completely neutralize our vinegar, we would do our stoichiometry, right? So here, this works out nicely. It's 1-to-1, but let's do it anyways. Actually, let's change this. Let's say we have 0.25 molar. Still a nice round number for us to work with, but we can emphasize the step here. All right, so with our stoichiometry, we always want to start with how much stuff we have. So we have 50 milliliters of 1 molar, which is 1 mole vinegar per liter. We want to do our stoichiometric conversion here. So again, these are both monoprotic, monobasic substances, which makes it easy. But if one of these was particularly our titrant, if our titrant is polyprotic or polybasic, things get complicated. If your analyte, the thing you're titrating, your weak acid, is polyprotic, things get much more complicated, and we're not going to worry about those systems in this course. All right, so we have 1 mole of NaOH per 1 mole of vinegar. Boom, boom. Maybe we'll color code this guy to match so that we know we're talking about vinegar there. And then this should all cancel, right? No, it doesn't. Almost cancels, right? Lastly, we need to deal with this liter versus milliliter mismatch. So to bring those units together, let's see, it doesn't matter which direction we go. I'm going to put 1 liter per 1,000 milliliters, right? And that'll cancel that out. And we just double check that things that needed to cancel. And why am I left with moles of sodium hydroxide? Because we're not done yet. All right, we don't need this step, right? So that would be if I wanted to know how many moles of sodium hydroxide I needed to neutralize this. But we're told the molarity of sodium hydroxide, right? So we can take that and we can convert 1 liter per 0.25 moles of sodium hydroxide, right? That's our concentration. And that'll tell us that in order to do this neutralization, we need 200 let's see, I guess we technically only have 2 sig figs here, right? That's telling us we need 200 milliliters of sodium hydroxide, right? Because that cancels, that cancels, that cancels, that cancels. In order to titrate this, and now we can start thinking. So if I add 200 milliliters, I'll be at that equivalence point, which is how much titrant we have to add to completely neutralize this reaction. If I add less than 200 milliliters, though, I don't quite make it, right? So I'm somewhere before the equivalence point. I'm going to have excess weak acid left, which means I'm going to have an equilibrium. And if I add more than 200 milliliters, I'm going to have too much, and I'm going to have this excess strong hydroxide, this strong base, which is relatively easy to think about. But let's doodle this. So if I'm talking about, in this case, milliliters and AOH, I'm just going to put 200 here. We already determined, we're going to have pH, that our reactions should start, our pH should start at 2.37, right? And what's interesting about this buffer is we're going to see a quick increase in pH as we add sodium hydroxide. If we have a pure acetic acid solution, that doesn't meet our previous definition of a buffer, right? We said a buffer, right? A buffer has weak acid and conjugate base present, right? Or we could flip that as weak base and conjugate acid present, but we have some mixture of those two so that we have both species ready to accept or donate protons to resist changes in pH. But when we're starting off, we don't have both of those present, right? So our initial pH is going to shoot up quickly because we don't have a buffer. Now, what's interesting is we've added hydroxide, right? So as we add in vinegar or hydroxide to vinegar, we see that conversion. Why don't we redraw our equilibria up here? Why don't we put them both here, right? So when we add our sodium hydroxide there, we're going to make this CH3COO, right? And maybe we should color code this to match. So if we add sodium hydroxide, that makes CH3COO, right? And if we remember our solubility, we know that sodium species are all super soluble. So this will separate into solution and make this CH3COO minus. So after adding some amount of sodium hydroxide, we end up with a solution that has a weak acid and the conjugate base present. So now we have a buffer. And we're going to see this very interesting region where we have some buffering happening, right? I'm going to have to move my metric, and then that region will have some curvature to it. It'll have some symmetry, and then we're actually going to see it shoot off again. So once we kind of get to the extreme end where, okay, now we only have CH3COO minus left, we're going to see the loss of that buffering capacity, and we're going to see that dramatic increase. And at some point on here, we're going to hit that equivalence point. Trying to decide what color to make it. We'll make it blue. All right, so that's our equivalence point. And after our equivalence point, we're going to see our pH continue to shoot up, and that's going to level off. It's going to creep up very slowly after that. All right, and it's going to approach some theoretical maximum. All right, so let's label these. This is our initial pH. In the center of this buffer region, so that's when we've added 100 milliliters. So we would call this spot the midpoint. This is our equivalence point. We can do some highlighting here, right? So we have everything to the side of our equivalence point. This will be one specific area a region of interest, we'll call it. We have this very finite little region here where it doesn't buffer well. And then we're going to have a nice region here centered around the midpoint where we have good buffering happening. All right, so a couple more fun facts here. At the midpoint, and if you know Henderson-Hasselbalch, this will make sense. We'll be at pH 4. Where is it? 7.4. All right, so this will be, because at the midpoint, the pH is equal to the pKa. All right, and that's interesting, right? Because that means if you can find your equivalence point, which would be this point of inflection up here, and you know you started with a pure compound, you can find your midpoint by just taking this 200 milliliter volume and dividing it by 2. And so if you're doing this experimentally, you're adding, you're watching your pH, it shoots up a little. Well, hey, let's turn on our laser. You're watching your pH, it shoots up a little bit at the beginning, and then it kind of levels off, and then you start to see it climb again, and then it really starts to shoot up. Boom. And now you're up here. I'm hoping you don't have to do any calculus to identify it in lab because that would be terrible. But visually, you can, just from your graph and your data, find this within a milliliter or two. And again, that's good enough, right? So then you find that, you say, okay, this took me 200 or 201 or 202 and divide that by 2. And you go look at your data point down there. If you have multiple data points on either side, but not it, you could, fit a line there and interpolate it. We could find that midpoint. So if you're solving experimentally in lab, which my standalone students are going to do, that's how you would do it. But we're here to talk about the math, right? So we already did our initial pH, right? And we'll circle these. So 1, that's the initial pH. We'll do the unbuffered region, which would be here and here, right? So 2. You have to use a rice table, right? So we'll do that. That's the same for here. We did a rice table. Your initial, obviously you have no products, but here you will have products, right? So you'll either have some if you're at the beginning or you'll have a lot at the end, but some amount of products are present. And typically, if you have more than 10 times as much reactant or more than 10 times as much product as the other one, you're no longer in this happy buffer region. You've moved completely into some region where the assumption that makes Henderson-Hasselbalch possible, which is violated. And that's why these regions don't behave like a buffer. If you are inside this nice buffer region, you can use the Henderson-Hasselbalch, right? And I apologize if there are umlauts and things in here that I'm forgetting. You can use the Henderson-Hasselbalch equation inside that region. If you're at the equivalence point, now things get weird. Let's put the 4 over here. So if you're at the equivalence point, this one's complicated. You need to use a rice table for the conjugate base. So we'll talk about that in a second. Well, probably a little more in a second. And then lastly, if you're beyond the equivalence point, you have excess strong base, right? So that means you just have to find the pH of your base. All right, so we have this nice rainbow collection here of things. We've already done number 1, right? So number 2 is really just an extension of number 1. So let's continue with our example here and connect each of these positions in the titration to an amount of titrant added, right? So this is 0 milliliters. So boom. So the unbuffered region, remember that has to do with this 10x thing, right? So if I add 1 milliliter of NaOH, let's just do it. Let's just at least get it started, right? So we already did initial pH. How do we determine if something's unbuffered? Well, let's say we add 1 milliliter of NaOH. What's the ratio of HA, in that case acetic acid, to A- or acetate? For titrations, it's really helpful to think, instead of concentration, initially at least, think in what is our moles and what is our volume. So what moles are present in what volume? All right, so if I add 1 milliliter of base to 50 milliliters of acid, and we assume volumes are additive, which these are aqueous additions, and they are similar concentrations, so it's probably the case. So that one's easy, right? We have 50 ml plus 1 ml. And if we want to really hedge our bet here, we could say that's approximately equal to 51 milliliters. So we have about 51 milliliters here. We want to know what amount of vinegar and other thing are present. So we're going to use these are like mole ice tables. All right, so we have our initial mole, our change in mole, our final mole for, HA, A minus. Do I need anything else for this? I feel like I'm missing a column. Oh yeah. We need our OH minus here. So we need to find out how many moles of OH minus we're adding. We're adding 1 milliliter times, and this is why I got confused earlier, 0.25 moles NaOH per, and I'm just going to write instead of liter down there 1,000 milliliters, right? Because those are equivalent. Now we have 1 times 0.25 divided by 1,000 gives us 0.00025 moles, right? And probably means we're going to need more space. So we're adding 0.00025. That's what we're starting with. Our initial concentration of A minus is going to be 0, and our initial concentration of HA here is going to be, same math, 50 ml times 1 mole vinegar per 1,000 ml. So we have 50 divided by 1,000, right? 0.05, right? And this is what we're starting with here. Now, this neutralization reaction, remember this goes to completion. All we do is we compare these two values, and whichever one's larger is what's left over. All right, so we're going to consume all of our minuscule amount of sodium hydroxide because 0.05 is much larger than that, and that's going to make A minus. And one of these two will always be 0 after a neutralization reaction. Either you used up all of the titrant or you used up all of the analyte. All right, so now we have 0.00 up, missed a 0.025, and we have 0.04975. So we want to know what the ratio of these is, and the easiest way to do that is to take the big number and divide it by the small number, right? So if we take that and we divide it by that, we get 199. All right, so that's saying we have 199 times more vinegar than acetate conjugate base, right? So if we have 199 times more vinegar than conjugate base, we're not in that 10x range. Like 199 is more than 10. So we would say we can't use HH here, and we'd go on to a rice table, right? And our rice table, we do want to be careful here, right? So we have our concentration of HA, our concentration of A minus, and our concentration of H plus. And now this is where titrations trip up people, right? Because our volume here is 51 milliliters, right? So even though we're starting with 0.04975 moles, remember, that is in 51 milliliters, or 0.051 liters. So as we add titrant here, if we're doing rice tables, our concentrations are changing. All right, so there's one concentration. And why don't we give ourselves some more space here and just solve for what that is. All right, so that's going to be 0.975 molar. I'm going to do the same thing here, right? We have that many moles over this many liters. That's going to give us 0.00490 molar. And we're going to start with 0 H plus. All right. And this is okay. It might feel strange. You might be like, we have H plus there, don't we? But this is okay for our titrations. We find out what are our initial concentrations and we work from there. All right. So we'll just leave that as a 0. Now we look at our change. Which direction do we expect equilibrium to go? We expect this to form H plus protons, right? So because this is 0, we're going to go that way. So we're going to have minus x, and at equilibria, 0.975 molar minus x. We're going to have this guy minus x, and we're going to have x there. All right, and remember our Ka is equal to 1.8 times 10 to the minus 5, right? So we can just set up our equilibrium expression. I said I wasn't going to do this, but now I'm curious what the pH of this system will be, because we just said this was unbuffered. So we do expect this to have a significant change on the pH. I'm just curious how extensive that effect will be. Now this one, notice that x here is inside expression, right? We have something minus x, so this will get very complicated. We would have to solve this with a quadratic, or as you guys probably can anticipate, we're going to solve it with Wolfram. Alrighty. Notice I'm very strict about my equal signs here too. You know, I'm okay with an equal sign here because these sides of the equation are equal, but I'm not going to put an equal here. I'm going to draw an arrow because this is not equal to x. If I write equal x equals something else, I'm not technically, those aren't truly equal. Will I critique you on your work if you show that? No. Oh, sorry, guys. All right, let's pull up Wolfram here. We're going to have 1.8 e to the minus 5 is equal to, get our top fraction. Parentheses are going to be super important here. X times x over 0.975 minus x. And that's going to give us imaginary roots. So what did I do wrong here? Usually if you get double imaginary roots, it means you set something up wrong somewhere. There it is, guys. There it is. Plus. So see, I know I was right. You made a mistake somewhere and it was that sign. And I'm sure if I did this in lecture, someone would have been like, Dr. Moore, please put a plus sign up there. And this is a good example that if we use technology correctly, technology doesn't let us down. We let down technology. All right, so now we have x is equal to 0.002. We'll take a couple, I guess, 240. We'll just call it 240, 24. All right, and then we take the negative log of that to get our pH, right? Because that's equal to our H plus concentration, negative log base 10. Log 10 of, we'll put the negative there. Now I want to be careful in saying that if you add, forget the negative there and you get a negative to like check yourself and assume, well, it's probably positive. You can have negative pH, but we're not going to see that in these weak acid base equilibria. All right, so we say 2.61. Does that make sense? Yeah, okay, wow. Yep, that's a big change. Yep. So that's our new pH. All right, and remember, our initial was 2.37. So adding one milliliter of 1/4 concentration strong base changed the pH by 24. That's a huge change. 1 milliliter. All right, so this region definitely not buffered. All right, so for our next region here, our buffered region, let's say we add a more reasonable amount. Let's say we add 75 milliliters of NaOH, right? We actually do the same thing here, right? We'd still have to start with our mole ice table here, and we have to find out what this ratio is. The difference is we'll just have different values in here. All right, so let's erase some stuff. And whenever you do these, I think it's easier to just keep recycling your old table and start from 0. You don't have to sequentially update these if you're doing a whole bunch of these. All right, so I want to know how many mole of NaOH is that. So we have 75 milliliters times 0.25 moles per 1,000 milliliters gives us 0.01875 moles of NaOH. All right, and we don't need that many sig figs, so we're just going to call it, okay, never mind. My heart of hearts does not feel good rounding until we get to the very end. All right, so again, we compare these two. This one's lower, so we're going to lose that amount from both sides, and we're going to gain that amount over here. So we're still going to end with 0 moles of OH minus, but now we're going to have appreciable amounts of other stuff left over, right? So 0.05 minus 0.1875. I have 0.03125, and we're going to 0.01875 over here. Again, we can just compare these mole amounts to find out what the ratio is. I like to divide the smaller one, the bigger one by the smaller one, just because it's easier for us to make sense of large numbers as opposed to decimals. All right, so that's 1.6x, right? And that is within 10x concentration. So we can use Henderson-Hasselbalch here. If we remind ourselves, Henderson-Hasselbalch is pH is equal to pKa plus the log of A minus over HA. So I can hear my baby babbling upstairs, and it is super cute. She's going over and over again. And now she's screaming. All right, so that's our Henderson-Hasselbalch equation. And if we remember from Henderson-Hasselbalch, because these are in the same volume, we can use moles instead of molarity. All right, because we could divide the top and bottom by the volume shared. And this is another reason sometimes we forget to include volume later in other steps. All right, so here volume doesn't matter because volume cancels. Here we have pH is equal to, our pKa was that 4.74 plus the log. So let's see, our HA goes on the bottom. Those, right, these are both in moles. So now we just do 4.74 plus the log of 0.01875, 0.03125. And that's going to give us a pH of, did I put those in wrong? Oh, nope, I did not delete the minus sign there. All right, there we go. All right, and just so we're clear, I was hesitating there because the pH was higher than the pKa, and it'll make sense in a second why that shouldn't be the case. So our pH is 4.52. All right, we only have 2 sig figs of significance, so we're going to call it there. Now, why didn't it make sense when we saw that other pH? All right, so one really good way of approaching these problems, which we already, did we do it somewhere? Where did we do that? Yeah, we did it here, right? Right. We determined our equivalence point, right? That 200 milliliters, which means we also know where our midpoint is. 75 is less than our midpoint. So we expect our pH to be less than our pKa, right? So in that other situation there, when our pH was 4.9 or 4.8 or whatever it was, that was above our pKa, which corresponds to a volume past the equivalence point, which is not what we were doing. All right, so always good to recognize these shenanigans when they happen. All right, so now is really probably the hardest part of the calculations, which is the pH at the equivalence point. All right, and the reason this is hard is because we have to change our lens. So far we've been looking at this wonderful reaction here. Our acid dissociating to form conjugate base. We've been using that to talk about what happens. And if we consider what we have at the equivalence point left over, so we're going to make our mole ice table again, right? It'll hopefully make apparent why this doesn't work so well for us. All right, and the math here is very convenient for us, and you'll see why in a second, right? So I could go through and calculate how many moles of OH minus here. But we already know we're at the equivalence point, right? So we have to have an equal amount, right? So it doesn't matter which side, they're both going to neutralize completely, unless I draw the number wrong. We're going to add 0.50 there, right? So now we have only acetate left, CH3COO minus. All right, so we only have this compound left. And if we try to write a Rice table here, we're going to have a problem. All right, but let's see what that is. So our Rice table won't work with this equilibria. So if we draw that, I already have the Rice table made somewhere, right? When we did our initial concentrations, let's pull that table. All right. And now we want to change these initial conditions, right? Because we want these to line up with what's we actually have. So we have 0 of this. We have 0 of this. And we have 0 of this. And this is where our problem comes up. Because now our next question is, which direction does this equilibrium go? Right? Well, we have no reactants, so it'll go to the left, right? But we also have no products, so it'll go to the right. And the answer is obviously neither of these. Like, this isn't the equilibria we're looking at. We're not looking at a weak acid dissociating anymore because we're looking at a pure weak base now, right? AKA the conjugate. All right, so this equilibria is worthless to us, right? We don't care about this anymore. We want to talk about what happens when we have a pure base. All right, so we want to flip our lens here, and this can be confusing. So if we think about what happens with a base, if we add a base to water, weak bases or bases in general take protons, so it's going to make BH plus and form OH minus. So now we just want to apply that to our equilibria. All right, so now let's draw out our new equilibria, but with our acetate, or CH3COO minus, acting as the base. So it's going to react with water to make, plus our vinegar. So we actually remake our vinegar here, right? So we can just make this into our rice table now. Boom. So now we know we're starting with, and again, what's our volume here, right? We added 200 milliliters, right? So we had to add 200 milliliters of NaOH to get here to our 50 milliliters of vinegar. So remember, our volume at EQ is going to be 50 milliliters plus 200 milliliters makes approximately 250 milliliters. All right, so now we're going to have 0.050 moles of CH3COO minus. But remember, that's in 250 milliliters, or, sorry guys, 0.250 liters. Water's a liquid, right? So we don't care about water. Let's just do something like that. We're starting with 0 CH3 and we're starting with 0 OH minus. All right. So this pH at the equivalence point is what tricks us. But now that we've made it this far, we can say, all right, we're going to move to the right. I have reactants. I don't have products. We can work with that. Let's calculate what this is. This should work out nicely, right? 0.05 divided by 0.25 gives us 0.2. All right, so we're going to lose some of this. We're going to gain some of this. We're going to gain some of that. And we're going to have 0.020 minus x plus x. We have to find our KB, right? So remember, our Ka described our weak acid dissociation, right? So that's fine, that's great, but that Ka doesn't apply down here, right? We need to know what's our Kb. And if we remember, we know that Kw is equal to Ka times Kb. Assume these are all capital Ks. So we get 1.0 times 10 to the negative 14 is equal to, I've been using green for our Kb, right? 1.8 times 10 to the minus 5 times Kb. And that'll tell us that our Kb is equal to 1 e to the minus 14 divided by 1.8 e to the minus 5. So we get 5.56 times 10 to the negative 10. Remember, our equilibrium constants are unitless, so we'll just leave it there. So now we have a Kb value here. We can get a pKb from that if we needed it, but we don't, right? So we're good to go now. So we're going to take our Kb, 5.56 times 10 to the minus 10 is equal to x squared over 0.20 minus x. We'll Wolfram alpha that. And again, always check your PEMDAS. Be careful when you're inputting these if you're not used to typing in stuff. You don't want to accidentally put the fraction in your exponent or anything. And we get a very, very small root, right? We get 0.000. How many zeros is that? Geez, 1, 2, all right. Let's just take that and let's see, I was really hoping for a nice, like if it would convert this to a scientific notation. I think we have 4 zeros there, right? 1, 2, 3, 4. You know, we could write that as 1.05 times 10 to the minus 5. And we want to be very careful here because we're not done yet, right? Because this is equal to our OH minus concentration. So we still have to convert this to a pH value. And that's where our, let's say that's yet another position that we can get stuck, right? So we get that concentration. We're like, oh, done, pH that. No, we're not. So I'm going to make it POH because I like to go personally OH minus to POH to pH. So our POH is going to be the negative log of that. I wonder if we highlight that and do that. I think it'll work, right? Yep. And we put the negative in front. So that'll give us 4.977. Now remember, pH plus POH is equal to 14. So we have our pH plus 4.977 is equal to 14. And we'll just go pH is 9.02. All right, and we have 2 sig figs, so we'll keep stopping there. All right, so this is an interesting point, right? We're now at our equivalence point here, and we've determined that our equivalence point was actually for this concentration acid. So depending on the amount of acid you start with and the concentration of your titrant, this value is not fixed. It's not like the pKa where you're at the midpoint, you're always at the pKa, the neutralization point, the equivalence point will move around. But right now it's 9.02. So we've fully neutralized our weak acid, but notice that that's not neutral pH, right? That's not pH 7. All right, so we're just going to make an emphasis of that, not. And here's something interesting. If I write that a little t, there's only a capital N. If I make it a big T, it's a capital O in the middle. All right, so not pH 7. All right, and that should, maybe we didn't anticipate that, but if we reflect on that, it can make sense, right? Because when we fully neutralize our weak acid, we're left with a base. And our base will have a basic pH, so it'll be a pH higher than 7. And that's always true. So all weak acids, when you fully neutralize them, create bases, and those bases, well, assuming they're monoprotic, those bases have, basic pH. The flip side is also true. If you have a monoprotic weak base and you fully neutralize that, well, now you're left over with acid, it's going to have an acidic pH. All right, and then we have our last step here. What number are we on? 5, excess titrant. All right, so let's say we add 300 milliliters of NaOH. And remember, our NaOH is at 0.25 molar, in case you've forgotten, because this is a very long video, apparently. So we know our first 200 milliliters is used to neutralize this. But, when in doubt, make these mole ice tables. Let's see, where's our favorite one to copy? Let's copy this guy. And we are going to be a little careful here, right? So let's calculate that. We have 300 milliliters times 0.25 moles per 1,000 milliliters gives us, so we have 300 times 0.25 divided by 1,000, right? So we have 0.075 moles of NaOH. And now we want to be careful here just to make sure we don't gum things up. So we're going to use up all our weak acid. And we're going to make all of our weak base. So at equilibrium, we're going to have 0 of that. We're going to have 0.025 OH minus. And we're going to have 0.050 A minus. And now the question is, what's the pH of this solution? And this is where we can overthink this, right? Because we've been in this equilibrium mindset. Rice tables, Henderson-Hasselbalch. I have to think about the equilibria. No, we're done now. We're done with equilibria. We have strong base present, right? We have 0.025 moles of OH minus. Now, is A minus going to pluck protons from the water and produce a little bit of OH minus? Maybe. Is the extent to which it's going to do that affect the concentration of 0.025 OH minus? No, absolutely not, right? Because it's a weak base, right? So when you have a mixture of a weak base and a strong base, the strong base determines the pH of the solution, right? So we know, right, that our concentration of OH minus here is equal to our excess moles in the volume. And again, we always want to keep in mind our volume is changing, right? So if we add 300 milliliters plus 50 milliliters, that gives us approximately 350 milliliters of volume. All right, so we take our 0.025 divided by 0.35, and we have a 0.071 molar OH minus solution. Now we just want to know, what's the pH of that? Well, we take the negative log of that, we subtract it from 14. So, and I'm just gonna, it's these exact same steps again. So I have 14 minus pOH, which is the log of, it's gonna be minus the log, right? Because we're moving this pH over there. So it's 14 minus pOH, and pOH is negative log of 0.071. So 14 minus the log of 0.071. And that's going to give us, all right, minus negative, right? So it's going to be positive. Again, so my hesitation here, is it possible to have a pH 15? Absolutely. Are we going to have a pH 15 from a 0.071 molar solution? No. In order to have pH 15, you have to exceed 10 molar OH minus. So again, we can check ourselves before we wreck ourselves or as we wreck ourselves. So 12.85 pH. All right. And there's something interesting here, right? So we're adding, at this point, our chemistry is done, right? We're really just, as we add more OH minus, we're increasing the amount of OH minus, we're increasing the volume. We're approaching a limit here. All right. So if we were to find out what is the pH of our titrant, there we know the concentration of our titrant is 0.25. So I'm just going to take this whole thing. I'm just going to put 0.25 in there. All right, and that tells us our pH will eventually go to 3.40. So if we go all the way back up to our chart here, our pH is approaching some limit up here at 13.40. So if I add infinite hydroxide, infinite 0.25 molar, really I would just be diluting my weak acid into a sea of base. And at some point, it doesn't matter. I've added so much base, I really have a nearly pure titrant solution. All right, so as we add more excess base, our pH will creep up to this value. Depending on what your tolerance is, eventually we'll reach it. But theoretically, we won't truly reach it, right? All right, so that is our journey through titrations. We'll cover this in lecture 2. I won't spend as much time on each part, ironically, just because we already know how to do some of these, right? But we'll, again, go over those tricks and those points of struggle that we encounter among students. All right, so hope this helps. Definitely encourage you to rewatch this video before your exam because, as I just said at the start of our video, titrations really sum up equilibria, and what is the point of an exam if not to test your knowledge, summing up everything you've learned? All right, so good exam 3 question, maybe not a final exam question. Maybe this is honestly a little intense for the final, where we are expected you to review many ideas and maybe not super focused on the end ones. Now, should you be able to do this? Yeah. Any other passing notes here I should mention? If you have a weak base, you're adding acid to it, it's going to look the same, but your curve is going to go down, right? Because if you're adding acid, your pH increases. We'll put a big squiggle here so we don't get lost. So definitely want to be careful of this weak base version. It's the same exact thing, slightly more painful because, for the first 3 of these situations, when we were, and again, I'm going to eyeball it here. That looks like an equivalence point to me. That looks like a midpoint to me. But when we were on this side of the equivalence point, we were calculating things in H plus for a weak acid. For a weak base, you're calculating OH minuses. So you're going to be working POH, and every time you have to convert to pH. The flip side is once you get over here and you do the equivalence point in the excess acid, it's already in pH, but do be careful of that. They're the same thing, different sides. You have to flip the conjugation when you're at that equivalence point. Don't forget that. And my heart of hearts says I'm forgetting something. Oh, I remember what I forgot, mole equivalence. So I was nice up here because we had a concrete example. I could write my axis of milliliters of NaOH, but usually we don't. When we talk about titrations, we talk generically about the titration. So we don't necessarily know how much analyte we have. We don't necessarily know the concentration of the analyte or the titrant. So we can't really make absolute axes. They have to be relative. So here I would say I have 0. Let's say I have, again, our titration of a weak acid. I would have my mole equivalence of OH minus. We're going to have the same shape here, right? We're going to have that buffer region, we're going to have some fall off, and then we're going to have something that creeps up. Now, what's interesting here is that our equivalence point, by definition, happens at 1. Our midpoint, by definition, happens at 0.5. And that's because a mole equivalent is defined as equal mole amounts of titrant and analyte. So if you have an absolute system, in our case, we had 0.050 moles of vinegar, right? So that just means 1 mole EQ then is equal to 0.050 moles. And that's it. That's all that a mole EQ is. I don't think you're expected to do anything, but if you had to transform your data from, say, moles of OH minus or milliliters of OH minus, you would use that conversion, or rather, this would be your conversion factor. All right, so you could say something like 0.050 moles of NaOH. Maybe we have, let's start with our backwards, right? We have 200 milliliters. We have our concentration, 0.205 mole NaOH, and we'll just call it OH minus per liter. Well, don't we have this conversion factor? And now these cancel, right? Mole OH minus cancels. Okay, whatever. We'll pretend that cancels. Technically, NaOH and OH minus aren't exact. We'd need something else to convert that, but we'll assume that's true. You know what? No, let's not assume that's true. Let's be really good people here. So we have NaOH, and I'm only doing this because if you have a polyprotic titrant like sulfuric acid or barium hydroxide, but if you have a polybasic titrant or polyprotic titrant, this matters. So we have 1 mole OH minus per 1 mole NaOH, all right? And we can go through, we can do that math, and it turns out that, this is equal to 1.0 mole EQ. And we're going to actually do the math because the last time I wanted to do an assumption like this, I had forgotten a plus sign somewhere. So let's clear this. 200 times 0.25 divided by 0.05 gives us 1,000. All right, so let's convert this to 1,000 milliliters because that's the factor we're off by, right? And now if we check this, milliliter, mole NaOH, mole NaOH, mole OH minus, we're left with mole EQs. All right, so we could convert, if we're starting from volume, we can convert that to mole EQ. If we're starting from a mole amount, we could convert that to mole EQ. Again, I don't think you'll have to do this in your lab, but we'll cover it just in case. Okay, so long video. I'll try to edit that down as much as I can. Good luck next week. This will definitely help with one of your homework problems too, so come back if you have questions and you're not quite sure from lecture. Also, you should have those lecture recordings, right? Our rooms are Zoom captured, so UD captured, I guess. All right, enjoy whatever it is you're going to do next, assuming it's not studying or homework. I mean, you can enjoy those too, but hopefully you'll have some better, more exciting stuff to do.